Okay, so for this new project, what I wanted to implement was a memory allocator. And yeah, here you can see it in action, I guess, in the array example. And I wanted to add it to our ds.h library so we can reuse it in other projects as well if we need it, because it's easier to have it once and not have to worry about it when we do WASM or other kind of projects where you cannot really use standard library. And yeah, the idea is we have to implement malloc and free from scratch, and then we can try to yeah, we can try to use that allocator in our examples from ds.h. And here I did this one by myself, but I guess it would be a good idea to try and let's say do the linked list. So basically the linked list, I guess it's more like the queue or the stack, right? Because I implemented the queue and the stack as linked lists. And okay, the idea is how does it work? Well, you have to first, I mean, if you are familiar with ds.h, you have to define the implementation. So let's say allocator implementation, and this will include all of the functions that are required to use the allocator, and it will also set malloc and free and realloc, obviously, to use the functions that I implemented, right? So I guess we have to do this thing, and then I mean, I have to copy a bit. Then we define some memory size, and I mean this can be, I mean I guess it can be anything. The only issue is that for arrays you need a really big memory pool because it will allocate at first like 8192 bytes or something, so I just put something huge there. So yeah. Then we need a temporary buffer, and this can be defined, I guess can be anywhere, but let's put it here. This is the temporary buffer where we are gonna write our memory. So this is some sort of simulation of the heap. This here we simulate our RAM memory. So we will be limited to only this memory buffer. So that's the first thing. Then we need the allocator, and we need to initialize it. So we create the allocator and we initialize it. I know it's a bit redundant that we pass the data and the memory size, um, but yeah, whatever, doesn't really matter. This is like the beginning of the heap of our RAM memory, and this is the maximum size. Yeah, I don't know. Then for doing the linked list, instead of calling to init directly, we need to call to the allocator version. And the allocator version gets in as before the queue. It gets the size of the elements. In our case, it's we use integers, and here it gets reference to the allocator. So we pass in the allocator, yeah, something like that. So now I guess it's a bit hard to see, but let's try to compile the entire thing and run the queue. Let's see if it still works. So I guess it still works, right? I mean, we get the same results as I haven't showed it, but I mean, it just iterates from 0 to 10. And I guess one thing we can do, we can dump the allocator and see how it looks in memory. I mean, we don't really have the data, but I guess we can see. I'm really curious. I guess I free the memory when I do pop, so let me just dump it here. So yeah, as you can see, we have like this is the memory address. Then we have I guess blocks on each memory address, and each block will contain the previous node, the next node, its size, and whether it's free or not. And yeah, I also implemented right like today did um, I guess you can call it like merging or coalescing the memory. When you free blocks, they group together into a single block, and when you find empty blocks, it splits them and uses just how much data is needed. But yeah, I mean, I guess it looks pretty strange at first, but if you also watch the implementation, probably it will make more sense because there I went step by step when I created this thing. So yeah, I guess. But yeah, this is like the memory mapping, and as you can see, after we free, let's say, because pop front also frees the thing. So let's do another dump here, and now you can see that the we only have a single block instead of having all of these small blocks. This is like the node, this is like the int, something like that, like it makes sense. And after we free everything, you can see that all the blocks are merged together. So that's the idea of instead of making each block free and keeping it by this size, we merge the adjacent blocks that are free. So that's like a small optimization. And I guess let's see what happens. I mean, yeah, I could also put a dump here. That way we can see it in action on each step. So something like first, after the first pop, we free the first block, and I guess it merges. Uh, I guess it merges some stuff. I'm not really sure. Probably like these for some reason. Um, but um, but yeah, I guess that's the idea. And maybe the other example from the allocator itself, where we say like, okay, we allocated 3 blocks, each has 128 byte size. Then we free the one in the middle. Then we allocate 32 and 8, so it allocates them here because it can split this one into multiple blocks. And then we free everything, so these merge together or something. So yeah, I guess that's the idea of the allocator. So now instead of using malloc and free, we can instead define this thing right here and then use our allocator. Yeah, which doesn't use standard library. So it is like, let's say, um, an improvement on when we are gonna do more WebAssembly and stuff. We can use this thing to allocate memory. So um, yeah, I guess I'll leave you to the implementation. So see you there. Okay, so let's see how I started out with implementing the allocator. First, as usual, the hello world message in C. So yeah, I put the code inside of this dynamic array library which I started a while ago, which turned out into these data structures, and I guess I'll add more stuff to it so it will become some kind of standard library. But yeah, I mean anyway. So for the memory allocator, I always saw that everyone starts out with some sort of linked list. So here I was thinking, can I reuse my linked list data structure? And I guess not really because, um, yeah, I mean, I want this block to be serialized onto a character array basically. So I want to have, let's say, a single array that will be a temporary buffer where the user will be able to allocate this array by themselves. So maybe put it on the stack, like create a char array and then pass that array as the buffer of memory to use by the allocator. So that's the idea. So yeah, how the block structure looks like. It's we need like a linked list structure. So we want to have a reference to the previous block, a reference to the next block. Then we also need the size of the block, like the size of the data that we allocated, how many bytes we can handle. Then we need, this one is not really needed right now, but it's nice to have a free flag which says if the block is free or not. Basically, when we are gonna free blocks, we are gonna be able to reuse them, right? So that's my idea how to handle freeing memory. We are gonna be able to reuse blocks and split them, merge them, um, do that kind of stuff with the blocks. So that's kind of the idea. And yeah, the allocator then, and here I guess comes in handy the fact that I played around with WASM, and there you have this heap start memory array, right? So at this point I was thinking, the allocator can be kind of like that. Like it can be a pointer to the start of the memory. Then we need another pointer to the top of the memory where we write new stuff. And obviously we need the size, how many bytes we can have inside of the allocator, how many bytes were allocated beforehand by the user of this library, something like that. So yeah, here I was trying to implement the block load and block write, so serializing and deserializing blocks. And I guess here I figured out that the best way to handle the linked list of blocks is to keep, instead of having pointers there for previous and next, I think it's easier to have indices in the data array, so just numbers. And then, because if you think about it, pointers are just indices. So, uh, yeah, if you implement your own memory allocator, for sure it's easier to use indices than pointers. So, yeah. So here I guess I did what I said about the allocator, thinking about it as having a start pointer and the top pointer, and probably here I changed it to uint, yeah. And I guess uint is not really the best because I also want to be able to show when a block or like when previous is undefined or null. And I guess in the end I decided to do it by using -1 as undefined, right? So yeah, yeah, like you need some sort of indicator that you don't have a previous, because if you use 0, 0 can mean both the first block because it's the index 0, or it can mean undefined, right? That's a bit of a trick when using indices instead of pointers, because pointers would be always different than 0. So yeah, I was stuck for quite a while on this block read and block write, but yeah. So I decided to split that into each field basically. So reading, being able to read the ints, being able to read whatever and whatnot. So yeah, here I was thinking how will the memory layout look like? It's not really, well, I mean, yeah, whatever. It's good for showing to other people how the memory layout looks like, but it's pretty obvious how it looks like, right? We have yeah. Here, what I wasn't sure about was, do I want to keep the data as little endian or big endian? Because if I serialize the data myself into that array, I can put it however I want. So I can implement both the read and the write however I want. But yeah, I mean, I decided to use little endian because why not? It's like usually when we work with memory, it's little endian. So
I wanted to keep it true to its standard library or whatever. So yeah, there I was just thinking how much memory each field uh, takes, and yeah, I started out I started to work on the right, but I don't think we need it right now. Like I should have started to work directly on the alloc and free because those are more interesting to be honest. And yeah, like at that point you would run into the need to write the serializing and deserializing for the data, but yeah, I mean you never know if you don't really need it. So yeah, I guess here I thought that well let's also have the top of the heap basically in the allocator. And yeah, we initialize the allocator, and the first time you create the allocator we will have the start and the top, they'll be on the same place, right? Because we don't have anything in the allocator or like in our memory buffer, in our memory array. So yeah, now at this point I started to work on the alloc function, which I mean it's the point of the entire series, I guess. So yeah, I was thinking just how trying to copy as much as possible from the malloc function to make it look like exactly like malloc. And I saw that in the standard library they use uint64 or like unsigned long. And yeah, I changed that. So I also needed a read function for uint64. And yeah, here I ran in I ran into this problem once before. Like yeah, I don't know. I guess it was just a warning. I think it would still work even without the casts, but it's better to add them just to like show what your intent was, right? I think that's the only reason to use the cast there because like the cast doesn't really matter if you think about it. Like the cast don't change anything. I mean, whatever. Maybe they do, and I'm stupid. Like maybe for unsigned and signed they change stuff, but I think not really. Like the memory, like the structure of the memory itself doesn't change, so that's why I'm saying it's pretty useless. Like only for printing, if you use different formatters, then it changes, and that's obvious that it changes because it's a different way of printing the underlying data. But I mean, yeah, whatever. So here I guess I was a bit ahead of myself with this allocator find block. We'll do that in the next part because I mean that's an interesting topic by itself. But for now, let's imagine that we don't do anything fancy or smart, and we just create new blocks each time we allocate, and the blocks that we free, we just forget about them in a way. Like we mark them as free, but we forget about them. We don't care about them. But in a smart way, you would reuse the freed blocks, right? Like if you want to allocate a bit of memory that's smaller than the free block, then you reuse the free block. Why not? Why create another block when you can reuse it? And yeah, here I thought that, well, I mean, probably I'll just have, instead of doing a pointer to a block, let's just use a simple variable because we don't need a pointer. And we'll change the allocator find block to return like a boolean value if it found or didn't find the block. So yeah. Okay, so I mean just initialize it with nothing because as I said that will be a to-do task, I guess. So yeah, now again just thinking a bit because like I was thinking about how to allocate a new block, right? So my idea was, well, if we don't have any blocks, then we need to do something different than if we have some blocks, right? But I guess we have a common part between all of them. So basically just setting the free status to 0 for the block, setting its size, I guess setting previous and next to null in in that's the idea. And I'm not sure what else was there, like maybe setting the data to null as well, just for the moment. I mean, we don't even need to set the data on the block. Like that's just for the structure to see how big it is, because the block itself is more like metadata. So I mean, even right now I'm figure realizing some stuff. So maybe the data like that uint8 pointer is not even needed in the block structure. Yeah, I think it's not even needed, to be honest. So yeah, maybe that's a thing to keep in mind. Maybe I'll remove it. But yeah. So yeah, because it's just like a pointer, but we don't even write to it. And when we allocate, we return. I mean, what's useful for is to be able to return at the end block.data, but you can keep it in a variable. You don't need to keep it in the structure. So yeah, whatever. So as I said, if I was thinking that if the block is the first block, then we can set previous and next to zeros, right? And I mean the next block will always be zero. That's something, because if you add a new item to a linked list, the last item won't have any neighbors on the next branch. It will only have neighbors on previous. So yeah, at that point, sure, I thought that we might need to read the previous block because we want to set its next value to the current one. So it would be something like, okay, the previous dot next should be, I think, allocator top minus allocator start. And if you subtract 2 pointers, then you get the index, right? Because you have a memory address at the start of the heap, then you have a memory address of where we are right now in the memory. And if you think about it, if you subtract those 2 pointers, you get the length from the start to your position. And by definition, that's like an index, right? Like that's where you are right now. So yeah, there I said the block previous. So oh yeah, so another thing that I thought that would be cool to have inside of the allocator is the address to the previous block. So instead of having only start and top, we also have previous, which is gonna be like one step before top, right? So that's the idea. And then we can use that previous to get the last block, and top would be saved for the current block. So yeah, a bit of a strange naming, but I I mean it makes sense, right? So start is the beginning, it never changes. Top is the current index, and previous is the previous index. So yeah, as I said, we set the block's previous index to be previous, and previous is next index to be the current one, to be the top. So yeah, and I guess after that we just had to increment to step previous one step. So that means setting previous to top and incrementing the top's position. And one thing to be careful about is to not forget about the metadata size, so of the block size, because you have to also add that, right? Because the metadata is saved in the heap, in our heap, let's say. So yeah, when we go to the next top, you actually have to increase it by size and also by the metadata size. Yeah, so that's one thing. And yeah, now I was just trying to create a dump function, so to pretty print these blocks from the allocator. And yeah, I mean, for the first one, it was just just write the stuff. And as you can see, like previous and next are just indices, so they show 0 when it's the start, and for the next it was showing 128. And I guess that's where you can see that the metadata size is taken into account, because the size of the data is only 100 for the first block, but the metadata is has size 28, so it's 128 for the next index. And yeah, here I was just trying to make a prettier print, if you will. So something like hex dump, but I mean, doing hex dump is uh, pretty would be pretty hard, I think. So because it's like aligned, and it also wouldn't really tell us much. So my other idea was print like a table. We're gonna have a header, right? So the header will be, previous, next, free, and size, or something like that. And yeah, basically that's what I was trying to do here, like printing the header with next, size, free, previous. We don't really want to print the data yet. I'm not sure how I will print the data though, because that would also be interesting to see, like the data itself. So yeah, here I was just playing around with the padding. You can do padding by doing that star. If you do percentage star s, then you have padding. So that's nice. And I think the padding is spaces. I have no idea, to be honest. But I mean, that's what it looks like. So yeah, like I decided on this kind of structure. So to have like the header up, and yeah, basically it's previous, next, size, and free. And then on each row we have the address of the I guess of the block, then the previous, the next, and so on. So yeah, here at this point I realized that the second block was showing null as previous. So well, I mean, first I did a free function, but free just sets the free flag to 1. So I guess that's the only thing we do for now. We don't do anything interesting, and I don't think it needs to do anything interesting. But yeah, here I realized that the second block was showing null as previous, and it shouldn't really do that. And it's because of this check right here. When we check if the previous is 0, then we do null. But here is where I was thinking, should I do -1 for undefined values, or should I change something else? Because if I do -1, then I have to change from unsigned to signed. And my logic was, well, if I change to signed, then I lose like a lot of potential numbers that I can use. But I mean, let's be honest now, it's kind of too big for this data structure. Like this allocator will be used like in only in small projects that cannot use the standard library. Like for example, for WASM, I guess I can use it. So that's the only place, and I don't think it's really needed to be able to allocate petabytes. And I only have like 32 gigabytes, so it doesn't matter anyway. And yeah, I mean, I guess I decided on using -1, and that was everything. And yeah, for the free function, we don't even need the allocator there, so that's something. But I decided to still check if the pointer was inside of the bounds, just to use the allocator, because why not? And yeah, right now we have a pretty decent place. Like we are able to allocate memory in the in a buffer, allocate it on the stack, for example. And yeah, like this should be useful for like wasm projects, right? Yeah, I mean here I was just playing around and seeing that if you make the buffer like let's say 100 bytes and you try to allocate 100 bytes, it won't work because it doesn't have space for the metadata. But like that's you cannot change that. It's the metadata is stored in the buffer, so you like this is the downside of this approach. Um, but yeah, I mean it is what it is. You cannot really change it. So yeah, I mean as I said, at this point we have a pretty decent start. We are able to allocate in a temporary buffer to free the memory, although freeing doesn't do anything yet. And yeah, in the next part I'll do more fancy handling of the free memory. So that's my plan. So yeah.
Okay, so in the second day, I wanted to do, as I said in the beginning, the splitting and the merging of the memory chunks. Like, if you want to allocate some memory and you have a block that is free and you find it, then why not just reuse it, right? And I guess an upgrade to that version, like on reusing on steroids, would be what if we actually, instead of using the entire block, we split it into a small block that we can use, and then the rest of the block would be left as a free block, and like the next time we find some use case for it, we can, use it there. So I guess first I was doing some test cases, preparing some test cases just to see if everything will work, and yeah, I decided to do like a few allocations, a few frees, see how it should look like. So yeah, and now I went into the find block function, and I think yeah, I started out by you know to search for a block that is free. You just have to. I mean, I should have iterated in the same way as for the printing because yeah, that's the easiest way to do it. I mean, in the end, I changed it to that iteration, like taking the pointer and then just adding size to it. So that's the easiest way. But the idea of finding a new block is to just, iterate all the blocks and find the first one that has free set to 1. And that's the first free block. And yeah, the idea is after we find that first free block, we have to split it into a size block. Like we get the size in the find function, so we can use that size to update its metadata, let's say. And after that, we have to add another block after the size is done. So maybe one thing to keep in mind is that when you split such a block, you have to make sure that you still have enough space for the metadata of the second block, because that's something we cannot go around, right? We have to also store the metadata of the blocks. So that's one thing you have to keep in mind. But yeah, right now this was a bit buggy because of the way I was doing the iteration, like the loop. So yeah, at some point I figured out that it's easiest to just look at the dump function and do it like that. Yeah, not really sure why I haven't figured that out instantly. Like it should have been, well, it's a loop over all the blocks. Why not just use that function? But I mean, anyway. So yeah, I wasn't getting the right I indices, so that's the issue that I had there. So to be honest, still not sure why it happened, but changing it to using the pointer from the dump function actually fixed it. So I have literally no idea why it was not working. But yeah, as I was saying, the you have to make sure that you have enough memory for the metadata as well, because otherwise it's you cannot really have a second block. So and like if you cannot have a second block, then you just reuse that entire space. You don't really have to split it anymore. So yeah, and I guess in my implementation, I put like let's say a threshold. I put like the threshold would be you need to have double the size of the metadata. I mean, you need to have at least 28 bytes left. I don't know. You can use +1 or something. But yeah, here I was overcomplicating a bit. I wanted to have a separate function for splitting, but to be honest, there's no point. You can do it inside of the if statement right there. Like the easiest way to do it. So yeah, after finding the block, you have to check for the size. That's the first thing you have to do. Let's see how long it took me in the implementation to do that. To write a simple if that just does if size is greater than block size. Or I mean, I guess I did it the other way around. If block size is greater than the size, plus metadata times 2. But yeah, I mean, just a threshold. So yeah, I mean, splitting, right? So you have to keep the old size just so you can go to the next block, because you have to also remember that this works as a doubly linked list. So you when you delete one element from the middle of the list somewhere at random, you have to update also the next block to point to the right previous, and also the previous block to point to the right next, if you catch my idea. So yeah, okay, yeah, finally I decided to not use a function and just you know do the right thing and just do an if statement right there. So yeah, if the current block is free and its size is large enough, we just create a new block. So I call this one split, and this is the block that's gonna stay free. And then our current block, we are gonna make it like I don't know, occupied or something. We put our data inside of that block. So yeah, yeah, there I said +1 or something. That doesn't matter if you. But yeah, the hardest thing here was to keep track of pointers and adding the right numbers. So I guess if you are really a beginner with pointers, this would be a really good practice to do something related to memory allocations, because it really forces you to think a lot of a lot about it. Yeah, I was losing my mind. So yeah, like it was. I mean, I got it almost first try. So yeah, but um, I mean, I was pretty sure that if I was really beginner, it would have been really painful to do that thing right there, to do all those pointers plus size plus whatever, just keeping a memory mapping of it. Like for sure, it would be a really good idea to have a lot of print statements when you do something like this, and print like both the pointers and also the indices. I mean, I also do that right here. I like sure, it's still hard even for me to keep track of all the pointers, but yeah, I mean, at least use printfs. Don't just do something blindly.
It's fine to use printfs. Why not? So to be honest, printf debugging is the best type of debugging. Like cannot really beat it unless you are really good at GDB or something. Like what's the point of going into GDB if you don't know how to use it? Like if you, I mean, if you want to learn it, then yeah, fine. But otherwise, why not just use printfs, right? And yeah, because it's less overhead if you use printfs, in my opinion. But yeah, after a while, I actually managed to do it. So I just had to also update the next node, and only the next node was required to be updated because when you split the current block, you add a new one after it. So the next block has to point to the right previous, which is the split one. Oh yeah, that's the only block you need to update. But yeah, after this one, splitting was working, and yeah, even if you add too much memory, goes to the right. It goes to the end, and it adds a new block. So yeah, it was working. So in the second part, I started to work on the free part, which, to be honest, this was the hardest one. But like looking at the times, this was the shortest one for some reason. But yeah, I mean, it felt like it was the hardest part because you have to update a lot of other blocks. It's again like the linked list, but like my idea for this one, how to merge the blocks was, well, if you merge them from the beginning, you don't have to worry about merging like extra special cases, like corner cases. So you have the block that you freed, it's somewhere random in the list of blocks. Then you have to check for the previous block. If the previous block is free, right, then you merge them, you merge both of them. And the idea is the previous node before your current previous, is gonna be 100% like in use. It cannot be free because if it was free, it was already merged. So it's either in use or it's either like the first one, and that's not there, right? So one of the two cases. So yeah, I guess the first step was to merge the previous node with the current one, and then for the next node is the same idea. If the next node is free, then the one after it is for sure is not gonna be free. So you can merge them safely. So yeah, and at first I did merging with next first, but I realized that if you merge with previous first, it's gonna be a bit easier because when you merge with previous, you actually move the data pointer backwards, right? You move it to the previous node. But when you merge with next, you don't have to move you just have to increase the size. It's like appending to a list. You don't really need to move anything around. So, but I mean, you don't have to move anything because it's freeing. It's not reallocating. But you get the idea. The pointer of the data moves, like the pointer of the block moves, uh, I guess both the pointer and the size change. And when you append next, only the size changes. So that's why it's easier to do previous first because it's gonna require like more changes. And next, if you do next first, it's gonna require even more changes. So yeah, because you have to update the next node twice. If you really think about it, like you have to update it first for the first merge and the second time when you merge with previous. So yeah, and if you merge first with previous, you have to update it only once when you merge with next. So yeah, so I can see that I finally switched those two around. But yeah, merging is like
as I said, you check if previous is free, and you have to set something like you set the size of the previous to be increased by currents, like the current block size plus the metadata. Again, don't forget about the metadata. Um, and then what you have to do is to say that the current block is actually the previous block. So yeah, basically you forget about the current block, and also you have to set next previous to be previous. Like that's the only extra thing. So it's exactly the same thing as working with the doubly linked list. So there I was like, whoa, it was working first try, but actually not. Yeah, it didn't work first try. I'm trying to remember what I messed up there. I think the order of the pointers for some reason. I mean, probably that was the fail I had. But yeah, when I had like 0 1 0 1 0, like in terms of freeing free status. So when I was trying to free the one in the middle, I was expecting it to merge with previous and next and be like 0 1 0. Yeah, like no, merge the three blocks in the middle together. So that was my hope there. But yeah, actually I know what the problem was. I was doing something like when I was writing the, but I don't think it was there. But when I was writing to block dot previous, so or something like that, and or when I was taking the pointer, the new pointer, I was doing block dot previous. I guess should have been something like block dot, yeah, yeah. So I was basically updating the block too soon, so that was the issue. But yeah, this thing actually fixed it, and yeah, now we had the allocator working properly. So I was just checking if the previous and next memory addresses are right, but yeah, those were correct. And I guess I also wanted to check if I can see anything wrong in the next check, but that one was fine. So yeah, basically this was everything for this allocator task. We managed to get the like an allocator working, and instead of using malloc and free, we can use this allocator. And I guess that's gonna be really useful for wasm projects where you cannot use standard library, and we have to use something like this. So that was the point of this project, to make it easier in wasm and projects like that. So